Okay, so let's revisit our prehistoric farmer, the one with the notches of their bone, and their flock of sheep. So let's say they started with 8 sheep. So one, two, three, four, five, six, 7, 8. And we'll say this is the bone that they have. Um, and let's say they get 3 more sheep. So they add one, two, 3 more notches into their bone. Because no longer, so suddenly, no longer the number of notches on their bone doesn't match the number of sheep in their flock. We can also show this with tokens as well. We could do something where we go 1, 2, 3, 4, 5, 6, 7, 8, and then we add an additional 1, 2, 3 to that. And we could simply count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we now have 11 sheep. But this can get cumbersome. So if we look, we can see that our 8 sheep plus our 3 new sheep gives us 11 sheep, which we can also represent with a 10 block and a 1 block. We can also write it using our special symbols or digits to say 8 plus 3 equals 11. This is our ones, this is our tens, and we're showing more succinctly or more simply what our equation or what our addition is giving us. I just want to take a quick side note to talk about this symbol here in particular, which is the equal sign. It's important to note that the equal sign always means these two things, so the things on either side of the equal sign, represent the same quantity. So whatever's on one side will always be equal to or represents the same as what's on the other side of it. Occasionally, the equal sign gets used to say this is similar to, or this is kind of the next step. But we want to make sure that when we're using the equal sign, we're actually meaning that what's on the left is equal to or the same quantity as what's on the right. As an alternative, if we're just going, this is the next step in something, we can use something like an arrow or occasionally an equal sign that's been turned into an arrow. So we can already start to see how math symbols and the terminology we use today were created to simplify math and to create a common language for cultures and societies to use. In our farmer example, a bone with some notches like this might work well when dealing with only a few sheep, but not when dealing with all the ears of corn in a crop. So numbers and symbols will represent we use numbers and symbols to represent numbers in their operations to simplify these things. This course is going to be using these simplifications, but also hopefully explaining a bit where they come from. So adding allows us to take 2 or more amounts and add them together or group them together to form a new amount or a total. Now, what happens if we were to take larger numbers? Let's say 1,234 plus 567. So we could represent this out with tokens. We probably wouldn't want to do it with tally marks or notches. It would take quite a while, especially the 1,234 to represent that. So instead, we use our numbers. And I'm actually going to start by adding these 2 numbers using an algorithm. So an algorithm is a set of rules or procedures that we follow when we compute something. Computers actually follow algorithms to solve all sorts of problems. And most of us were probably taught algorithms or rules or processes or procedures to follow to solve most of our math problems. In the case of addition, you were most likely told to write the larger number on top, an addition sign, and the smaller number on the bottom, adding up the ones, the tens, the hundreds, and so on. And then you would go through and you would add. So 4 plus 7 is 11. You carry or regroup the 1. This gives us 9, 10. We regroup or carry 5, 6, 7, 8, and finally a 1. So using this kind of algorithm or procedure, we can add 1,234 to 567 to give us 1,001. But why does this actually work? Where does the carrying and regrouping of these numbers come from? Is it something we just memorize and do? Or does it actually represent or mean something? Well, algorithms are great shortcuts to help us solve problems more quickly. They don't actually tell you the process or the procedure and why it works. I really want to focus this course on breaking down these processes and showing representationally where they come from. So let's start with this example. We can rewrite 1,234, and notice I'm not using an equal sign. So we can represent, oh, actually, sorry. We can use an equal sign because this is the same as 1,000 plus 200 plus 30 plus 4. Now, you may have seen this written as 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4 times 1, which is a perfectly valid way of representing. But because we're starting just with addition, I'm not going to add in the multiplication model for it just yet. But what this does tell us is we have 1,000, 2 hundreds, 3 tens, and 4 ones. Now, if we write the number 567, we get 500 or 5 100s plus 60 plus 7. And just to make it a bit clearer, I'm going to make sure that these line up so we can see our ones, tens, hundreds, and thousands all nicely lined up. So let's look at this using our tiles. So we can see at the top level here that we have 1,000, 2 100s, 3 tens, and 4 ones. We'll zoom in a little to make it a bit clearer. And we are adding that to 5 100s, 6 tens, and 7 ones. So what we do is we now bring these together. So we bring our 4 and our 7 together to give us this row here. We bring our 3 and our 6 together to give us 9. We bring our 200 and our 500 together. So we've grouped them together this way. You'll notice that the addition sign doesn't exist here anymore. So this is both of these groups put together. So that gives us a total of 9 100s. And then we still have our 1 1000 here. We can then go through and regroup. So at this point, we have 11 ones. So we can create an additional 10, leaving our 1 here. And now this also gives us a 100. So we can bring this over, leaving us with our final answer of 1,000, 800s, 0 tens, and 1 1, which is what our answer shows us, our 1,801. So when we add these together, this gives us 11. This gives us 90, 700, 1,000, but we take this and we make this into a 1. We add our 10 here to give us 100. And again, we go 1,000 plus we now have 800s plus 0 tens plus 1, or 1,801. And we can see this up in our algorithm represented by our regrouping. We had an extra group of tens or ones, so we moved that over into our tens. We had an extra group of hundreds, extra group of tens, so we moved that over into another group of our hundreds and moved this up. So our algorithm is basically simplifying our representations by using numbers and symbols. One thing that I want to state is it's important to note that we could have done this in a different order. I could have started with the tens or the hundreds, added those, and then worked my way backwards. But that would have meant that I would have had to have gone backwards and kind of cleaned up any remainders. So, from a simplified way of looking at it, starting with the ones, or to the very right of the number and moving left simply saves us a few steps at the end. We can also see when we break it out like this that lining up our place values is incredibly important. Otherwise, if we lined up the 2 and the 6, we'd be trying to add 200 to 60, and we wouldn't get our correct answer. And this is a common mistake that students often make when they're adding in this way, because if they don't see the importance of lining up the numbers by place value, by breaking out and seeing what each of the numbers actually means, then they may not line things up properly, and they may try and add hundreds to tens, giving them the incorrect answer.